Now let us discuss about the chapter chemical kinetics. So what do you mean by kinetics in general? Kinetics is nothing but the movement of something. Now the chemical kinetics as a whole means that the movement of a chemical reaction, that too with respect to time. So the most important variable which is involved is time here. Now in this chapter we'll be looking into the rate law. Then we'll be looking into order and molecularity of a reaction. Then we will derive some relations based on it and solve numericals. Then we will get into the Arrhenius concept. Then we will look into the collision theory. At last, we will look into the Van Hoff's equation, which is nothing but a derived concept of Arrhenius equation. So now let us look into a simple reaction. Say suppose A gives B, where here the reactant is A and the product is B. Now, how do we write the rate equation for this equation? Now, the difference in concentration of A with respect to time t should be equal to the difference in concentration of B with respect to time. Now, why is there a negative sign here? Because the reactant concentration decreases as time proceeds and the product concentration increases as time increases. Now, but then the magnitude of both the rates remain the same. This is a simple equation. Now this can be written for complex reactions as well. Say suppose the reaction is like this. Now how can we write the rate equation? Now it can be simply written as 1 by A times dA by dt is equal to 1 by B times dB by dt. Same applies for the product as well. But then one should take care of the sign which is involved, whether it is positive or negative. Now here capital A and capital B are reactants and capital C, capital D are products. Now small a, small b, small c and small d are nothing but the stoichiometric coefficients. Now here in this equation, what basically we are doing is we are calculating the rate of a particular entity which reacts in a reaction per the stoichiometric coefficient or per mole. So here it is just a basic mix of the stoichiometry and the rate equation, nothing else. Here we are dividing. If we are calculating the rate of A, reactant A, how the concentration of A changes with respect to time, we are dividing it by the stoichiometric coefficient of A. And if it is for B, then B, and so on for all the reactants and products. Yeah. So now let us see what rate law is. So rate law basically relates rate with the reactant concentration. The most important point to be noted here is it is only the reactant concentration and not the product concentration. So now how can we express it mathematically? Now rate is directly proportional to, say suppose the reaction is A gives B. Rate is directly proportional to reactant concentration to the power of some x. So now this x can be any real number. Now how can we write? By introducing a proportionality constant. So rate is equal to some k times a power x. Now this k can be specially called as the rate constant. We introduce it a name called rate constant. Now this has a lot of significance. We'll look into it later. Now this k is called as rate constant. This is nothing but the proportionality constant, but then we call it as rate constant. Now this is the rate equation for this particular reaction. A gives B. So this X has also a specific name, that also we will look into it. So now this is a simple reaction. So what is the rate equation for a complex reaction? Say suppose A plus B gives C plus D. Now the rate can be written as K times A power X into B power Y, where X and Y belongs to real number. Now this is the rate equation. So this is basically rate law. Now we can look into the order of a reaction. So what basically is the order of a reaction? Order of a reaction is nothing but the power of reactant concentration. So that term which we looked into in the previous rate law explanation, which was called as X, that is nothing but the order of that reaction. So the same reaction A gives B. There we express the rate equation as rate is equal to some k times A power X. Now this X we term it as the order of a reaction. Now this order of a reaction can be an integer or it can be a fraction as well. So now, so this is the order of a reaction for a simple case. Say suppose there are two more reactants. Say suppose A plus B gives C plus D. Now how can we write the rate equation? Rate is nothing but k times A power some x into B power some y. Now there are two variables here, x and y, two real numbers. Now how can we define the order of this reaction? Now here there are some terminologies to be understood. Now there are two orders here. One is the order with respect to reactant A, and the second one is the order with respect to reactant B. So order with respect to reactant A is nothing but the power which is involved with the reactant A. So that is nothing but X. Now order with respect to reactant B is nothing but Y. So there are two orders here, but then we define one more term called total order. So if in case they ask the order of this reaction, then the answer should be X plus Y. So order with respect to reactant A is nothing but X. That is the power of A. We call it as order with respect to reactant A. The same applies for B as well. But then the total order or simply the order of the reaction is nothing but X plus Y. Now we can redefine the order of a reaction as the sum of the uh, the sum of the powers of reactant concentration. So order is nothing but sum of powers of reactant concentration. Reactant concentration in what? In which equation? It is nothing but the rate equation. Rate equation in the sense which we discussed in the rate law. Yes, so this is all about the order of a reaction. Now let us come to the molecularity of a reaction. So molecularity of the reaction is nothing but the number of reactant molecules which is involved in a specific reaction. Or simply we can write it as number of reactant molecules. Now the most important point which is to be noted here, which we can consider as a difference between order and molecularity, is molecularity is always a whole number. That is, it cannot be a fraction or something, it cannot be a decimal. But then order of reaction can be a decimal as well. Now, the order of a reaction can change with respect to time in a particular reaction, but then molecularity of a reaction does not change. So, now let us classify the reactions based on their order. So, they can be classified as zero order reaction, first order reaction, second order, and so on. So, now we will be looking briefly into the zeroth order and the first order reaction, and we will derive the common case as well. So now let us look into what zero order reaction is. Now as the name suggests, zero order reaction is a reaction where the order of that particular reaction is zero. Now say for example, let us take this simple example. A gives B. Now according to the rate law, we can write its rate to be K times A power some X. Now this rate can also be written as the difference in concentration of reactant A with respect to time t. Now, since the reactant concentration decreases with respect to time, let us introduce a negative sign as well here, since the rate is negative. Now, let us name this equation 1, name this equation 2. These both equations are same. So, we can equate the right hand sides of both these equations. Now, by equating these, we get dA by dt is nothing but minus k times a power x. Now, since this is a zero order reaction, x is 0 here, since we defined this x to be the order of a particular reaction. So, now dA by dt is nothing but minus k times a power 0, which is nothing but minus k. Now, by bringing t to the dt to the other side, we get dA is equal to minus k dt. Now let us integrate on both the sides. Now the concentration, let us assume the initial concentration to be A naught. So we have to integrate from A naught to some final concentration, let us say A. Now time starts from 0 to some time t. So by integrating, we get A minus A naught is equal to minus k times t minus 0. So A naught minus A is nothing but k times t. So this is nothing but, this equation comes into use for solving many numericals. So this is the equation for zero order reaction. From here we can find out the rate constant of a zero order reaction. A naught minus A by T. This is the rate constant for a zeroth order reaction. Or if you want to find time, you can interchange K and T. So this equation as a whole comes into use for solving many numericals. So this is an important relation. So let us introduce another term as well here. That is nothing but half-life of a particular reaction. So half-life of a particular reaction, it is not specific for zeroth order reaction, but then it is a general term. We used to denote it by T half. So half-life of a reaction is nothing but that instant of time when the initial reactant concentration gets halved. So that is nothing but if the reactant concentration initially is A naught, then after time t, the reactant concentration A naught gets halved. That is, the reactant concentration becomes A naught by 2. Then that time t is nothing but the half life of a particular reaction. So say suppose, let us explain it through the zeroth order reaction. So say suppose we consider the same reaction A gives B. Now the expression of the zeroth order reaction we have already defined, we have already derived is A naught minus A is nothing but K times T. Now at time T is equal to T half. Now say suppose T half is the half life of this particular reaction. Yes. So now at time T is equal to T half. Now what will be the final concentration A? The final concentration A will be nothing but half of the initial concentration. So now substituting these on our primary equation, we get A naught minus A naught by 2 is nothing but K times half life. So the final concentration is nothing but A naught by 2. Only that change we are doing with a particular relation. Now we get A naught by 2 is nothing but K times T half. Now half life is nothing but A naught by 2K. So this is the half life of a zeroth order reaction. Now let us do the same for the first order reaction as well. Because in numericals, particularly in JE, you get a lot of numericals based on zeroth order and first order. Now for first order reaction, the same definition holds good. Here the order of this particular reaction is 1. So now let us consider the same reaction A gives B. Now let us apply rate law for this. Now rate is equal to some K times A power X. Now this X here is nothing but 1, and rate can be written as minus dA by dt as discussed before. Now we can write the equation as minus dA by dt is equal to minus K times A power 1, since the order of the reaction is 1 here. Now let us bring the A to the left hand side. So dA by A is equal to minus K dt. So integrating both the sides from, and the concentration from A naught to A and the time from 0 to t, we get, so the integration dx by x is nothing but natural logarithm of x, natural logarithm of mod of x. Similarly here, by integrating it, we get the natural logarithm of the variable a, the limits from a naught to a is nothing but minus k times from 0 to t. Now we can write this as natural logarithm of a by a naught. So this is by using the property of logarithm. Log of a minus log of a naught can be written as log of a by a naught. So that is the thing I am using here. So log of a by a naught is equal to minus k times t. Now bringing the negative sign to the left hand side, we get minus log of a by a naught is equal to kt. Now if there is a minus sign here, now we can bring that to the power here. So this becomes log of a by a naught to the power minus 1 is equal to k times t. So we get the final equation as log of a naught by a is equal to k times t. So this is the equation specifically for the first order reactions. So this relation is also used in most of the numericals. Here this is the natural logarithm to the base e. Now if we convert it into the logarithm to the base 10, we have to introduce a new constant 2.303 log of a naught by a is equal to k times t. This relation also comes into use, where mostly we solve numericals by taking to the base of 10. So here the a naught is the initial concentration, a is the final concentration, and t is the time t which the reaction takes to convert from the reactant concentration A naught to the final concentration A. Now similarly we can derive the half-life equation for the first order reaction as well. So going by the definition, half-life is the time required for the reactant concentration to get halved, that is to change from A naught to A naught by 2, and the time changes from 0 to the half-life which we are required to find. Now going by the relation of the first order reaction which we have just derived, it is nothing but log of 2.303 into log of a naught by a is nothing but k times t. Now here if we consider the final concentration a to be a naught by 2, then the time automatically becomes the half life time. So 2.303 log of a naught by a naught by 2 is nothing but k times half life. So this a naught and this a naught will get cancelled, and finally we get 2.303 times natural logarithm of 2 is nothing but k times half life. So 2.303 times ln 2 by k is nothing but half life. So this 2.303 into ln 2 is nothing but 0.693. So remembering this value gets into use for solving many of the numericals. So in general, the half-life of a first order reaction is nothing but 0.693 divided by k, where k is the order of the reaction. So the most important point to be noted in this relation is the half-life of a first order reaction does not depend upon the reactant concentration. So this is the only order of a reaction whose half-life doesn't depend upon the reactant concentration. Yes. So let us derive the general case as well. So let us look into the general derivation. Say suppose for nth order reaction, we'll get an important proportionality relation as well from here. That is why we are deriving. So say suppose A gives B. Now the general reaction, the rate equation can be written as dA by dt is equal to minus k times A to the power of n. Since we are taking the order to be n, now this is nothing but the modified rate equation. This we already know. So now following the same steps by bringing back A to this side to LHS, we get this relation. Now we will integrate the same way from A naught to A and from 0 to t. Now by integrating we get a to the power of minus n plus 1 divided by minus n plus 1, and the limits are from a naught to a, that is nothing but on the other side minus k times from 0 to t. So now simplifying this relation we get a naught to the power 1 minus n minus a to the power 1 minus n by 1 minus n is equal to k times t. So thus we have derived a general equation for any reaction whose order is n. So here if we substitute 0, we will get the equation, the relation which we have already derived for zeroth order reaction. So this relation also comes into use for solving most of the problems. One can always derive based on the rate law. If one remembers the basic rate law, we can derive for any reaction. So here we can derive the relation for half-life as well. So half-life is when the final concentration becomes the half of the initial concentration. Now substituting this relation in the general equation which we have derived just now, we get a naught to the power 1 minus n minus a naught to the power a naught by 2 to the power of 1 minus n divided by 1 minus n is equal to k times half-life. So simplifying it, we get the relation of half-life to be 2 power n minus 1 minus 1 into final initial concentration to the power of 1 minus n divided by 2 power 1 minus n into 1 minus n. So this is the general half-life equation for any reaction whose order is n. So here the general observation which is to be noted is half-life is directly proportional to the initial concentration to the power of 1 minus n. So T half is directly proportional to A naught to the power of 1 minus n, and we can also say it as half-life is directly proportional to 1 by A naught to the power of n minus 1. So this also comes into use for solving various numericals. This is for an nth order reaction. So now we have successfully looked into the zeroth order and first order reaction. We have something called pseudo first order reaction as well. So pseudo first order reaction is nothing but it is a special case of first order reaction where the concentration of one or more reactant is sufficiently large such that there is no significant change in the concentration of those reactants when compared to the other reactants. So we can understand it with respect to an example. So the example of this pseudo first order reaction is nothing but the very famous equation which is the hydrolysis of ester. Now this equation is nothing but, now say suppose we can consider this simple ester whose hydrolysis equation is given by this, which breaks to give acetic acid and ethyl alcohol. Now in this reaction what happens is we usually add excess of water. So if the concentration of water is sufficiently large, then as the reaction proceeds, there will be no significant change in the concentration of that particular reactant. So say suppose the concentration of water is very large, and let us understand by taking an example. Say suppose we increment the number 1000 by 1, we get 1001. So this doesn't make a very significant change. So this is nothing but 1 by 1000. So this 10 power minus 3 is very less when compared to 1. So similarly, as the concentration of water is very large, as the reaction proceeds, the concentration of water does not change much, as the concentration is always large. But then the concentration of this ester is less when compared to water, is very less when compared to the concentration of water. So the change in concentration of ester becomes significant in this reaction. So now usually we write the rate law equation for this reaction as rate is equal to some K times the concentration of this ester into the concentration of water. Now as we know that the concentration of water is a constant, now we can combine it with this constant. So K times the concentration of water is also a constant. We can take it to be K dash or something. Now the rate can be written as some K dash times the concentration of the ester. So this equation which we have written here resembles somewhat to the first order reactions relation. So this is similar to the first order reaction, because there we had K and here we are having K dash, which is a combination of K and the concentration of water, which is constant. So now this has become a first order reaction where only the concentration of ester changes. So now this can occupy the place of A, which we used to derive the previous relations. So now since rate is equal to some K times the ester concentration, now it resembles first order reaction. So these type of reactions are basically called as pseudo first order reaction. So this can also happen with the reactions of other order also. Now this is just an example to understand. So this is all about the first order and the zeroth order reactions. Now there are second order, third order, first order reactions as well. Now if we are asked to solve some numerical of that kind, we can always substitute the value of n, which is the order of the reaction, in the general case we have derived just before discussing this. So now let us solve some numericals based on what we have seen just before this. Now let us consider this question. If the unit of rate constant is liter square mole power minus 2 and second inverse, the order of the reaction is. So now for this reaction, for this question, what can we say? We can make use of the general relation we have just derived. Now the general relation just says that K times T is nothing but A naught power 1 minus n minus A power 1 minus n divided by 1 minus n times T. Now we are asked the unit of the rate constant. We are given the unit of the rate constant. So let us bring the variable t to the other side. If we bring t to the other side, we get k is equal to a naught power 1 minus n minus a power 1 minus n divided by 1 minus n times t. So now as we can clearly see, the constant we know already the unit of the concentration, which is nothing but mole per liter. Now we can concentrate on calculating the unit of this particular relation, unit of K based on this particular relation. So mole per liter to the power of 1 minus n divided by second. So this is nothing but the unit of K with respect to this relation. So now we get, by simplifying, mole power 1 minus n, liter power n minus 1, and second inverse. Now this is the general unit for any particular rate constant. So if we substitute the value of n here, we get the unit of the rate constant of that particular reaction whose order is n. Now this is given in the question to be liter square, mole power minus 2, and second inverse. Now we can equate the power of the liter or mole or second. Now 1 minus n is equal to 2. Sorry, 1 minus n is nothing but minus 2. So n is nothing but 3. Now we can also use this relation. We can also compare the power of liter, n minus 1 is equal to 2. From here also we get n is equal to 3. So the order of the reaction is nothing but 3. So let us move on to the next question. Consider a reaction AA plus BB gives same thing. Now if dA by dt is equal to K, some K, and dB by dt is equal to some H, then the ratio of dd by dt is to dc by dt is equal to option A C by D, option B BH by AK, option C AHD by KCB, and option D AKD divided by HCB. So now in this question we are asked to find this ratio. Now seeing this, we can almost decipher what the question is expecting from us. Now we are given dA by dt and dB by dt. They are asking the ratio of dd by dt is to dc by dt. Now we have already learnt a relation which connects all these rate dA by dt, dB by dt, dc by dt with respect to the stoichiometric coefficients. We already know that relation. So we can apply that. Minus 1 by A dA by dt is equal to minus 1 by B dB by dt is equal to 1 by C, dC by dt is equal to 1 by D dd by dt. So now here we can equate this and this and this and this alternatively. So now if we equate that, we have already been given that dA by dt is nothing but K, and dB by dt is nothing but H. So now we can connect this, the first term and the third term here, and write it as minus 1 by A into K is equal to 1 by C times dC by dt. So now dC by dt is equal to minus Kc by A. Now this we can keep it as equation number 1. So similarly, we can compare the second and fourth term here and write dB by dt was H. So hence we can write minus 1 by b times h is equal to 1 by d times dd by dt. So now dd by dt is nothing but minus h times d by b. Now this we can consider to be equation number 2. Now we are asked the ratio. So the ratio is nothing but equation number 2 divided by equation number 1. If we divide, we get the equation to be dd by dt into 1 by d divided by, so basically we are dividing equation 2 by equation 1 here. So what was the equation, previous equation? It was, yeah, kc by a here. So yeah, so here dc by dt into 1 by c, this is nothing but which is equal to h minus h by b and minus k by a. Now here I have actually brought d to the other side here, so that is why I am writing only minus h by b, otherwise you have to include d here. So by simplifying this, we get the ratio to be dd by dt is nothing but, after cross multiplying, we get it to be ah d divided by kcb, which is option number C. Now this is our next question. Consider a reaction of first order A gives B. Now after 15 minutes, find the percentage dissociation of A, and our half-life is given to be 10 minutes. Now, how do you find the percentage dissociation of A? So say suppose this reaction is given already, A gives B, and at time t equal to 0, say suppose the concentration, say suppose the number of moles of reactant A is small a, the product side it will be 0, and at time t is equal to 15 minutes as given in the question. Now say suppose uh, factor x has been reduced, and so the same factor x would have been added in the product side. So this is the general procedure we follow. Now the percentage dissociation, here it is defined as the difference in the number of moles of the reactant divided by the initial moles of the reactant, which is A, times 100. So this is what we are asked to find. But now here we can relate only to the concentration. But here we have the relation which contains the terms which indicates the number of moles. So here we divide the numerator and denominator like this by volume. So this relation still doesn't change. Yes. So A minus x by V is nothing but, now it is the change in the concentration. We can keep it as delta A, and A by V is nothing but the initial concentration, which is A naught. So now we are asked to find delta A by A naught times 100. So now this delta A, we can further write it as A naught minus A. So now the given uh, answer, the given solution becomes A naught minus A divided by the initial concentration A naught times 100. So this is what we are asked to find. Now let us further divide numerator and denominator by A naught. So what do we get? We get 1 minus A by A naught divided by 1 into 100. So we are basically asked to find 1 minus A by A naught times 100. So we are doing all these manipulations just to find this ratio, because only we know this ratio Uh, we already know the first order reactions relation, which is nothing but ln A naught by A is equal to K times T. Now in the question, they have given the half-life to be 10 minutes. Now we already know the half-life of a first order reaction is nothing but ln 2 by K, which is nothing but 10 minutes. So K is equal to ln 2 by 10. Now time they have already mentioned after 15 minutes. So this T becomes 15 minutes. So logarithm of A naught by A is equal to ln 2 by 10 into 15. We get by substituting all these. Now by further cancellation, we get 3 by 2. Now ln A naught by A is equal to 3 by 2 times ln 2. Now applying the property of logarithm, we get ln 2 power 3 by 2. Now 2 power 3 by 2 is nothing but ln 2 root 2. So since the first term and the third term are the same, so A naught by A is equal to 2 root 2. So we have found the ratio of A naught by A. Now in the previous slide, we have reduced this relation. So this is why we reduced to this relation, because we had to find this ratio A by A naught. Now we have found A naught by A. So it is just the reciprocal. So in the question, they have asked to find us 1 minus A by A naught times 100. We have already found A naught by A to be 2 root 2. So the answer becomes 1 minus 1 by 2 root 2 times 100. So the final answer is 2 root 2 minus 1 by 2 root 2 into 100 percentage. So this we can calculate.